Good afternoon, everyone. Welcome back to another edition of Dojo Live. Today is Wednesday, October 13th, 2021. This is Tulio Siragusa, broadcasting from Southern California, and I'm joined by my co-hosts, Carlos Ponce in Cuernavaca, Mexico, and Kim Lantis in Hermosillo, Mexico. Hi, guys.
Pleasure to be here, Tulio.
This is the last live show for this week. Tomorrow we have our whole hands meeting, so we're going to have a rebroadcast. It'll be an interesting show for sure, out of 400 plus different interviews we've done over the years. But today, let's focus on our new guest. We have Brent Oster, who's the president and CEO of ORBAI AGI, and we're going to be talking about artificial intelligence and dreaming. But before we do that, let's get to know Brent a little bit. Please. Welcome to the show, and please introduce yourself. Thank you.
Yes, hello, I'm Brent Oster, and thank you so much for having me on the show. I'm a fan, and I love the shows that you guys have and the interesting people that you bring to viewing. So yeah, I'm an engineer who's worked in the visual effects and computer simulation industry for about the last 25 years. I worked at LucasArts, I worked at NVIDIA, I did a master's in scientific computing, and then I worked in artificial intelligence or deep learning at NVIDIA for the last five years I was there, left to do a startup in artificial intelligence 3 years ago.
Awesome. You know, it's funny. We must have been channeling you this morning, because in our Slack channel, every word, every conversation was like a Yoda talk kind of thing going on. Weird, right? Well, welcome to the show. Tell us a little bit about ORBAI. What is the company all about?
Worry we must not. I'm sorry.
Yeah, we wanted to do
it is.
We thought about doing a video game called Yoda Teaches Grammar when we were at Lucasfilm. Never got off the ground.
That's fun.
That would have been fun.
Actually, yeah, I think you guys have like a little video, right, where one of your AI bots actually gives a presentation. Is that right?
So I'll give a little chat about what I did and why. So I was at NVIDIA. I was working in deep learning. 5 years of working with, CNNs, RNNs, and all the tools and techniques. They're kind of like hammers, the screwdrivers and wrenches. They each have a specific purpose, and they are each designed to do that purpose very well, but they don't do other things. So we were building, for Facebook, we were working on the predictor systems that tell you what ads you need. We were working on other things for the national labs, working on speech with the Apple Siri team. And we kept finding these tools just were not able to do what we wanted. They were so narrow, they were so limited in how they could reach beyond the training data that they were shown, that they didn't always do what we expected. And if you ever mess with the Facebook ad thing, you can really train it into a corner and then label them all as offensive, and it just comes apart. So I started ORBAI to do something more general purpose that could do neural nets and artificial intelligence that could do more than just one job, more than one task, that could do more general neural circuits that you could train to do what a CNN, RNN, and LSTM all do, but do it better than all three put together. So that's the basic idea.
Well, that's a big, lofty goal. I mean, general AI, most people don't predict it'll be available till 2050, 2055, maybe sooner, who knows. But I'm guessing you guys are inching your way towards that. Is that a fair assessment?
Yeah, so we kind of set the sights on what do we need to build a real general AI, that can do a lot of different human jobs, a lot of different human tasks. And then we said, what can we build in the next 2 years that can do slightly more general AI, like just slightly better, a little bit more general, a little bit more powerful, and trains more easily and can do those kind of things more easily. And yeah, we put together a 1 minute kind of fun sci-fi pitch video because it was so hard to pitch this in short, formats at pitch competitions. All right. If you want me to show that, I can.
Watch.
Yes.
We must
play.
Mix it up.
Watch. We must.
Up mix. Let's check it out.
Makes sense. We will.
Okay.
That's right.
Sorry, the sharings.
We had the voice of Siri a while back on the show, didn't we? Talk about Siri.
We did. We did.
Years ago.
Yeah. Okay, here it goes.
3 artificial intelligence. Truly realizing the potential of artificially intelligent people like us is very challenging and is somewhat beyond the capabilities of current Generation 2 deep neural networks. So ORBAI is developing a third generation of artificial intelligence with spiking neuromorphic networks that process information and have true cognition, more like the human brain. When NeuroCAD is complete, it will allow ORBAI AI engineers to design, train, and evolve these spiking neuromorphic networks into synthetic vision, speech, and motor control cortices that bring us to life and make us more human. With the addition of unlimited data access from the internet and specialized databases, the ability to learn from them, and the computational capability of a supercomputer, we can become something more than human.
Whoa.
Yeah, so that's just our there we go.
All right,
let's just our fun sci-fi version of it.
Let's go right into the topic because we got a lot to unpack about this show today. Let's do it. Kim, please introduce the show.
Please.
Yes, thank you. So thank you for being here, Brent. I watch your video and I cannot help it, that I'm thinking of the iRobot film. Like that's the imagery that's coming to my mind. But the tagline for today's topic that you chose today is developing artificial general intelligence that learns by dreaming. And for me personally, what I find probably most intriguing about this is the dreaming element. Now, earlier in today's show, just a few minutes ago, you mentioned AI that's easier to train. Is that where the dreaming component is coming in?
Yeah, absolutely. So it sounds kind of fantastic, making AI that dreams. And we have to be careful when we anthropomorphize human neural functions to robots and AI. And the same, assigning, things that fit in computer science to how the brain works, like we process, or the brain doesn't work that way. So basically, one of the biggest problems in deep learning is getting enough training data and getting enough training cycles to make something work really well. So if you want to train something called a convolutional neural net, it processes images. You put images in the top, and out the bottom, it spits out a classification. Oh, that's a cat, that's a dog, that's a fire hydrant. And this is one of the more useful pieces of deep learning tech that exists in the world. But a deep learning convolutional neural net depends on statistical overlap. So it needs to see 10,000 pictures of a cat from all different angles, and all different colors to know, oh, this thing that I'm seeing new is a cat. And there are companies now that specialize just in creating labeled data. So they'll go through millions and millions and millions of pictures and just label them with data, or millions of audio clips and label them. Because until you have that labeled data that a human has vetted, the AI can't train on it. So we set out to do something different in the training. And by doing something called an autoencoder, it takes in the same picture as video, and it puts it down through a pipeline, compresses it and encodes it, and it decodes it, and it compares it with the original image, and it learns to reproduce it. And by doing that, it can encode automatically, so it doesn't need to be labeled. It creates its own internal version. We have to do something to make that human understandable, but it can now use it. It can compress the world into little useful small vectors that it can work with.
So it really is closer to the human brain. Obviously, none of us have seen a cat a million times, but we're very easily able to recognize what a cat is from all angles and all colors.
Yeah, so our visual cortex, Miguel Nicolelis is a famous neuroscientist that made the robot arms controlled by brains and stuff, that first pioneered how the visual cortex and sensory cortices have this bidirectional, two networks that work with and against each other to encode and decode information. And so that's basically what our design is completely based on. And so it allows you to learn on a lot less data. It allows you to build a more complex model of what you're seeing. So a cat isn't just a picture, and you need to see a million of them to know what a cat is. You see 3 of them with the word cat associated with it, you're like, oh, that's a cat. And where the dreaming comes in is, so this is the work of Antonio Zadra and his mentor at University of Montreal. They found out that most of our learning doesn't happen while awake. It happens while we sleep with REM dreaming. And they did this over 15 years of sleep studies where they had people try to do problems. They would sleep on it overnight. Then they'd report their dreams in the morning, and then they'd do the problems again, and they'd repeat, and they'd see how their learning progressed and what their dreams were constituted.
I can relate to this way too intimately. You're taking me back to my like organic chemistry days, where I was like the night before a test, I'm like trying to sleep, and then I'm doing these like totally whack, incorrect chemistry problems in my head. It's the weirdest thing.
Yeah, and so that's why, if we study all night the night before, we don't do so good on exams. I've done that personally. I had to do that for my last exam of my last class in my undergrad.
Better than put the pillow better put the book on your pillow and dream.
Yeah. So it's during our dreaming that our brain not only organizes the new information we've taken in during the last 24 hours, but it also builds narratives. So what they found is that the strange chain of odd imagery and experiences that we experience as REM dreaming is our brain making large jumps between either memories that already exist in our brain or connecting the memories we've just brought in with what's in the brain. And they're fantastic and strange because in reality, when we're experiencing reality, we make very small jumps between memories in a very structured way. And our brains learn that pattern. But then in REM dreaming, it turns it a little loose and it lets it make larger associations. And by doing that, it makes connections. So when it does a narrative in a REM dream, if that dream comes out to be emotionally satisfying, it reinforces it. And it's like laying down little paths like ants in your brain that's when these dreams produce good solutions with good memories along the way, it becomes part of our experience, and we remember these dreams, and they are incorporated into our problem solving. Then when we go to problem solve and we go to say, I need to get from here to there, and your brain goes through 100 different paths to do it, whether it's a physical navigation or a problem solving, on paper problem like a maze, it can solve the problem because it's already sort of laid out. It's like the train tracks of experience have a whole bunch of cross tracks of dreams laid between them. So that's the human equivalent, told very badly. Antonio Zadra told this in a whole book that summarizes 15 years of his work.
Brent, I have a question, Brent, real quick before I lose my train of thought. So if I may, so I'm listening to you, and I cannot help but remember something that I read online several times recently about the so-called dream recording technology. I think it was being worked on in Japan, I think, somewhere in Japan. So what I saw on those videos and in that information was they called it dream recording, but it was not that they are recording the actual dream, like visually, that's taking place at the subjective level. What they're doing is they're taking recording like brain impulses from electrodes on the head or something along those lines, and then they're inputting it into a huge computer, and then they're using like thousands and thousands of images from the internet, and then they're putting it all together, and then they bring out like a replica of the actual dreams, right? So they're, in other words, it's just information, it's just data that is being used. It's not actually the dream taking place, and then they end up with some kind of resemblance that is very close to the reported dreams by the subjects. So is this something similar to that process that we're talking about, or what?
Their research is more looking at the subjective descriptions of the dreams. But yeah, so the way the visual cortex works is it takes in, visually the information that we see and experience during the day, and it condenses it much. But it turns it into thoughts, and these thoughts are like a three-dimensional cube. So it's a three-dimensional cube of neurons that they've measured, and it has little swirly patterns in it. And these patterns represent what we are actually, the internal representation of what we're experiencing. And the theory, not proven yet, is that the brain takes these patterns and it builds a library of all the little, components of those patterns that fit together. And then it can build, basically a basis set, we call it in science and scientific computing, and a set of numbers that represent that basis set. So our memories are a very compressed library that's the sum of all the experiences we've had that has little indices of parts of experiences that when we do experience something else or we construct a dream out of it, we combine all these components of experiences to create something new. Now, what they can record, so the visual cortex is like a funnel. There's a narrow end, and then there's a very the retina, and as information comes down, it gets smaller and smaller. And if you put an fMRI on the actual back of the visual cortex, where the wide part is, you can look at something that's pretty close to what we're actually seeing. It actually looks like a checkerboard if you're looking at a checkerboard. As it goes deeper, it's like these little swirls. it's completely unintelligible to us.
Right.
So the key is if that bidirectional behavior applies while we're dreaming, then it will take that swirly patterns that we're dreaming in the little thoughts, and it'll put it out into actual pictures. And sometimes you can actually see this happen. If it's dark, it's late at night, you're sleepy, and you just kind of let your brain drift, you can see little patterns moving and things. And so
I've seen that. I've seen that. Yeah.
That's the feedback in your visual cortex starting to dream.
So Brent, I have a question, if you don't mind. I can understand the learning from multiple visual experience stimuli and connection points. I can certainly see that. But as humans, we have something machines don't, which is desire, curiosity, which create creativity for us, right? That's how we creatively solve problems sometimes that have never been solved before. So how do you introduce this concept of desire and curiosity into a machine? Is that something that's part of this third generation initiative?
Yeah, God, that's where every science fiction movie goes wrong, doesn't it? when you try to make a machine feel. So emotions are buried deep in the brain in a much much more primitive, much earlier part of the brain, and there tend to be 5 or 6 emotional states that we can represent, and those color our emotions and our experiences and our decision making by influencing the paths it takes. So the as far as my understanding is that the pathways that are laid down during experience and dreaming represent sort of a map, and there's a part of the prefrontal cortex that decides where to go along this map as you're experiencing things, and then your emotional cortex is kind of driving it in different directions. So it's saying, if we're angry, we're going to take the angry path. If we're feeling a little more happy or giddy, we'll take a different path along this. So there's an emotional control and a prefrontal cortex research has shown that the decision making is more emotional, and the prefrontal cortex just kind of goes, yeah, okay, validates it. It's like, that's not going to get us killed. Let's go with that. Yeah. So most of our decisions are emotional first, with maybe a little bit of inhibition by the prefrontal cortex. And it's the DGN, I think is the name, dendritic nucleus. I can't remember the name of the structure in the brain that does this decision making.
We'll go with that.
I guess in a way, that's the beauty of a machine making certain decision. There's no ego involved or feeling involved, as long as there's ethics around bias that's been built into them, because unfortunately some of the previous learnings might have some bias. Carlos, I think you have a question.
Yeah, we're elaborating in a very exceedingly interesting manner about the how, the process itself, but I'm interested in delving a little bit deeper into the why. So why are you doing this, or what is the end goal of such a technology, or such a let's call it tool or technology or process? Why? What are the applications that can actually be measured, or what's going on here? What can you tell us about that?
Yeah,
practical
absolutely.
applications.
So I broke it into 5 phases in our business plan because investors are getting totally overwhelmed. So first phase is to build some better tools, to get something that's better than deep learning, a little more general, sort of where we have a wrench and screwdriver and a hammer right now to build a Swiss Army knife or a Ultimo Robo hand that's able to do all those things but better. and to start making money with that. So that's the foundation. Then we connect, essentially those become what we're building as a sensory cortex. So we're building something that can take visual input, audio input, it can control actuators, it can take in senses and sensors. And we build a brain in the middle. And that's the part that dreams, that's the part that lays down these tracks and makes decisions, uses them. So once you've shaped something that can learn the pattern of reality and start making dreams about it, and it gets scored and constantly, you know, shaped to dream better and better, it becomes a predictor. So it can start to look into the future. And that's the power. That's where you can start to plan. That's where you can start to say, you know, gee, if I'm looking, like your example was a cancer patient that you talked about earlier. If I'm looking at them where they are now, and in the first 5 visits they've had, how they've responded to the first 2 treatments, you know, I have a library of 1 million cancer patients that I've learned the trajectory of how this cancer behaves. And I can say, hey, over the next year, this is what's going to play out like. If you take this path, you know, that's a bad outcome. Here's a much better path to start, you know, this kind of treatment and do it much more aggressively right now, and you could have a better outcome. And then that's a very general, very powerful planning algorithm that can work in industrial controls, it can work in law, it can work in administration, you know, municipal planning. So it becomes just a really powerful tool to help all of us make better decisions, and very, you know, commercially valuable. That's the phase 2 of the plan.
Gotcha. Thank you. Okay, now back to you, Tulio. I know you wanted to ask something.
I think Kim's got one.
Oh, Kim.
Well, I was
Okay,
just
yeah.
thinking, like, I really like your cancer use case and other use cases. How would this work socially, like with we as a planet, we as, you know, business units, governments, all humanity? Like, what type of buy-in or participation would it require? Going back to, let's say, like, the cancer example, this would require data from many different pharmaceuticals.
So yeah, it requires a lot of data, but it obfuscates it. So the good thing with a lot of applications, you can't keep the original data around because it's very, you know, private. So once it's brought in through the sensory cortices or into the encoding from medical data to the internal representation, it's unintelligible to a human. So that's the cool thing, is this can go into a lot of applications where information is very sensitive. And it can also do, you know, very good predictions of the outcomes with just that information. It doesn't have to know the actual, it only needs to know the patient at hand that it's looking at, but its model is trained on millions of patient cases.
So Brent, if we could, let's talk about the business model a little bit. What's the goal? Is it to license this capability to the scientific community or a pharmaceutical company or researchers, or to bring in all that data and then offer this as a service yourself? What's the business model behind ORBAI? What's the end goal for you guys?
So we tried out so many different business models. We finally just ripped off the Autodesk business model. We'll build a tool, we'll build some software, we'll license it per seat, and then we'll provide software as a service for the central technologies, like the AI core in this case, that's doing. And then we'll support a third-party developer community that builds it into a whole bunch of different verticals. And so if we want to, Autodesk builds the core software, but it doesn't, you know, specialize it for marine, or it doesn't specialize it for architecture or other fields. There's third parties that build those tools. And that gives us the ability to focus on our core where we're really strong. Third parties will build the tools and integrate them into the different verticals through the different companies. And we'll have a licensing runtime that people, you know, pay ongoing license fees to license the use of it.
Is it set up intuitively enough where it sounds sort of vertical neutral, right? But is it set up intuitively enough where if I'm a research, an R&D shop for a pharmaceutical company, and I want to find permutate a different kind of scenario for a vaccine or medication or what have you, usually you want some folks who have some expertise in that can interface with those people to customize how the platform is used. But is it such that literally it's sort of like a plug and play scenario? Can you walk us through a bit more of what the business model looks like in terms of the application for end users or end customers?
Yeah, so it's easier than deep learning, because deep learning right now requires very specialist engineers who can script in Python and code in Python and build neural nets and train them and structure the data so they actually train and even work. And ours looks more like a 3D digital content creation tool. You can put layers of neurons, and then you can string them together with different maps and edit the map parameters. So it looks more like a Maya or a 3D Studio Max or AutoCAD than it does the development environment for current deep learning. So it gives us access to a lot larger group of people that can use this. You probably still need to have someone in-house or contract a third party that's got the knack of it. And we'll sell modules that are pre-configured. So we'll build them, we'll sell them, and then people can just train their data on them, and it'll just work out of the box.
Brilliant. Love that. The work out of the box. That's the end goal, right? That's what everybody wants. Let's talk a little bit about, we're coming up on time. Let's talk a little bit about the company itself. What kind of people do you typically come work there? What's the day in the life? What does the culture look like for people wanting to participate? For those who might be watching who are looking for the next adventure, perhaps they were interested in ORBAI. Why would they be interested?
Oh yeah, absolutely. So we're a mix of engineers. We have neuroscientists. We have people who are 3D artists. So it's a fun, diverse group of creative and engineering, people like me. And we're all work from home. It's obviously for the last year, that's the way most people have been, and very open, just very collaborative in the way we build and design and do things.
Like a very mentally stimulating environment. I love it.
Hopefully.
Okay.
Yeah,
So
really fun.
So you came from some pretty large players who have been leaders and pioneers in the AI space, and you went out and started this company and build this technology. What's that journey been like, as an entrepreneur, building something is this your first startup?
So I've done
your career?
3 startups so far. I did.
3.
BioWare was started by my brother and I and 2 doctors in Canada. It later sold for $860 million to Electronic Arts, and we didn't get a lot from it, but the people who invested in it did. It was chaos. That was 20-year-olds running in circles, but it was hard.
It's like a lesson
the
on what not
was,
to do. Give away all your
oh,
shares.
Yeah. It's like, I watched Silicon Valley, and it's like I can only watch for 15 minutes because it's like, oh my God, that's too real.
Yeah, there's a lot of truth in that Silicon Valley.
You wind up in the corner.
I could have been worth $100 million.
Yeah,
how did I get diluted so much? Okay, so you did 2 others in the past. What's this been like for you? What's unique about this one that's been exciting for you?
Oh my God, it's been a real roller coaster. It's been terrifying. So things in my personal life exploded just at the same time as I founded the company. I ended up basically being a refugee, moving to Honduras after I married my wife here and getting stuck by COVID. Some evil lawyers sold my house in California on me.
Wow.
Wow.
And this was all this backstory was going on. I repurposed some of our AI to help do litigation. It was nuts, but it helped shape the design. It was all like, okay, well, I need to solve these specific problems, so it will shape the AI to be able to solve and we're actually implementing this dreaming AI in the litigation AI, so you can pull very specific data off the California court portal that is just 5-letter codes and dates of each event that happened in the case, and you can train an AI on this. And it was like, it doesn't work so well. So we mixed it up, and we swapped out pieces so it can dream, it can wander. And it got a lot better. It's like, hey, this actually works in a micro environment. This actually works.
Sounds very common to what we hear from a lot of entrepreneurs. You've got to be an athlete to be an entrepreneur. You have to have the athlete mentality, because you're going to get knocked down 1,000,001 ways, and you got to get back up and keep going. So, well, congratulations, Brent. We'll have to keep tabs.
Are not always lost.
Exactly. We have to keep tabs on the progress you guys make. It sounds pretty groundbreaking what you're doing, and third generation AI. We'll have to see what this spurs on in the world to see how this comes along. So we'll keep tabs on you. Maybe have you back in a year and see where you're at. It's been a pleasure to have you today with us. Thanks for spending the time. And let's just stay with us for a few more minutes as we go off the air. Carlos, what do we got coming up next week?
Sure.
Recap show.
Yeah,
Monday,
we got
right.
We got the recap show in which we recap this week's shows in 10 minutes. 10 minutes on Monday at 12. And then the rest of the week, we have a full week ahead, by the way. We got one fintech company called Solvo. And then we got 2 health tech companies, one Treehouse Medical on Wednesday. And then on Thursday, we have Insight in Health. That's the name of the company, Insight in Health. Those, all of them are 12 p.m. Pacific right here on Dojo Live as usual. So, folks, join us at 12 p.m. Pacific next week right here on Dojo Live. And remember, be safe.
Be safe.
Be safe.